Hi, I'm Gail Lock-McDowell, author of Crackling Coding Interview. In this video, I'm going to talk about bubble sort. So bubble sort is not the most efficient algorithm. In fact, it's pretty bad. It's an O of n squared algorithm, whereas we have other algorithms that are O of n log n. So it's not the most efficient, but it's one that is fairly intuitive and it's one that we talk about a lot. And so it's worth being familiar with what it is and how it works. So let's dive in.
This array is obviously unsorted. So what bubble sort does is it just repeatedly walks through the array, swapping things that are out of order. And then when it's all sorted, we're done. So let's show you how this works. Here is my swappy doodad. Is 5 and 8 in order? Yeah, actually it is. 8 and 9? Yep. 9 and 2? Nope. Let's swap those. All right. 6 and 9? Yep. Now, you might be wondering, why are all of the elements white except for 9, which is pink? And this is not a mistake. This is done intentionally. So 9 is the biggest element in the array. And I want you to kind of keep an eye on what happens with 9. Okay, so 9 and 7. Yep, nope, that's on order. Let's swap those. 9 and 3, out of order. 9 and 1, out of order. 4 and 9, out of order. Okay, now note how 9 kind of latched onto us. And once we found it, there is no letting go of it. It will keep walking through our array with us, forcing us to swap it every time, which means that actually everything, well, from 9 on, is in order. In other words, 9 is in place right now. Awesome. Okay, so that was our first pass. Let's do it again. 5 and 8, in order. Yep. 2 and 8, nope. I'm going to have to swap those. All right. 8 and 6, nope. 8 and 7, nope. 8 and 3, nope. You know what? I want to make 8 pink because I want to show you what happens here with this 8. I'm just going to make a little line there. All right. So 8 and 1, nope. 8 and 4, nope. And look at that. 8 is now in place. So again, the biggest element latched onto us and wouldn't let go, but now everything from there on is in place. But we're not done yet. The array is still out of order. So 2 and 5, nope. Gotta swap those. 5 and 6, all good. 6 and 7, great. 7, 3, nope. All right, 7 and 1, swap. 4 and 7, swap. Again, that biggest element latched on and wouldn't let go. So now everything from here on is in order. All right, another pass. 2 and 5, all good. 5 and 6, great. 3 and 6, nope. 6 and 1, nope. 6 and 4, nope. All right. Now again, everything from 6 on is in place. 2 and 5, all good. 5 and 3, nope. All right. 5 and 1, nope. 5 and 4, nope. All right. Now again, everything from 5 on is in place. Let's try again. 2 and 3, great. 1 and 3, afraid not. Okay. 3 and 4, all good. Okay. 1 and 2, nope. 2 and 3, yep. All right, everything from 3 on is in order. Now, as you can see, actually, we're actually should be done. Our entire array is in order, but we don't actually know that until we make another pass and we're like, and then after that, it's like, oh, hey, we actually never swapped anything, so we must be good to go there. So we need to do one more pass. Then if we had to do no swaps, then we know everything is done. Okay, so this algorithm ends up walking through the array n times and making, it's actually repeatedly smaller and smaller passes. So it's n elements at one time and then n minus 1, then n minus 2, and then n minus 3. So what we're doing is 1 plus 2 plus 3 plus 4 plus 5 ... steps all the way up to n. So if you remember that old equation, the sum of values from 1 through n is n times n plus 1 over 2. So that's O of n squared. So that's our runtime. Space complexity, though, is constant time. All right, so let's see how to implement this. All right, so here's my basic code here. I have already an array kind of set up, and I can call this. So let's dive into the code. So with bubble sort, we're going to want to make repeated passes until the array is sorted. So let me have a flag called sorted, and I'm going to keep looping until it is sorted. So I'm going to start off with this being false, and it's going to keep looping as long as it's not sorted. All right. I can delete that line of code now. Okay. And now I'm going to want to do my loop. So I'm going to start off with it. I'm going to say, hey, this is sorted. Pretend it's sorted. Let's see what happens. And then here I'm going to do my loop. So what is it going to loop through? So it's going to loop through index from 0 until what? Well, at first glance, I might try that. And the reason why I have a -1 in there is that I'm going to be swapping each element with the next element. And so I don't want to go out of bounds. And so I want to stop, actually, my index should stop at the second to last element. So that's why I have a -1 in here. And actually, that length thing isn't quite right. And I'm going to come back to that and fix that in a moment. Okay, so walk through the array, and this is where I do my sweep to swap elements. So if this array, if this index is greater than, if this element is greater than the next one, then I want to swap the array. And so I'm going to throw this, I want to swap this index, this element with the next one. So I'm going to throw this into a separate function just because it's easier to read and it also demonstrates good modularization to the interviewer. So swap first and second index. Okay, so to do this, swapping is pretty straightforward. Get the first element, set the first element equal to the second element, and then change that element. Okay. All right. And then, all right, so I'm back here at swapping. If I needed to swap, then the array is not sorted. And okay, that looks pretty good. So I'm actually just I'm gonna come back and I'm gonna want to change that in a moment. But just real quickly, I'm just gonna see if that runs. All right, it successfully sorted it. Code isn't quite as efficient as it could be. Because remember when we walk through an example, we could sort of say that after each sweep, the kind of right part of the array is fully sorted. So I'm going to call it final index. So final index is going to start off as length of array -1. And so I want to go until then. And then after each sweep, pull that index in by 1. Okay, so let's hope that still works. Aha, excellent, it did. So this algorithm isn't the most efficient by any means. It's an O of n squared algorithm, but it's useful to know. We kind of reference it a lot when we talk about different sorting algorithms. So not the most efficient, but it is useful to know. And it's a good way to just sort of get your feet wet with sorting. So go ahead and try this out on your own code as well.
Hi, I'm Gail Locke McDowell, author of Cracking the Coding Interview. Let's talk about what merge sort is. Merge sort is a very popular algorithm for sorting. We use it quite a bit, and it works by, well, doing a whole lot of merges. And it's a fairly intuitive algorithm, but not one you would have immediately jumped out at you as a thing to do. So let's talk about what merge sort is and how to implement it.
So merge sort works through divide and conquer. It basically says, hey, this big array, it's too big for me to handle. But if you sort the left half and you sort the right half, I'll take care of merging them back together. Of course, how do we get the left and the right half sorted? Well, by the same approach. So then it gets this little array of size 4 and it says, too big for me to handle. Let me you sort left half, you sort right half, and I'll merge them back together. And if we do that over and over again, eventually we get down to just 2 elements at the very bottom. And of course, we can just merge those back together. That's not hard. And so that's how we do it. We apply this recursive approach. We divide in half and divide in half and divide in half until we get down to just this little base case of just single elements, and then we merge them back together. And so we sort left, sort right, and merge them back together. So now that we have the idea down, let's see if we can code this. All right, so we have our skeleton code, so let's just dive in. So as we recall, merge sort needs to sort the left, sort the right, merge them back together. That's the idea. So I'm going to need left and right indices, which I cannot do right with this method because I want to give people just like a general merge sort method to call. So I'm actually going to need a left and right index. And so I'm going to change this to merge sort helper, left and right. Okay, now if I've only got one element, if I have one or less elements, one or few, I should say, elements left in the array, then just return. So I'm going to write this so that the left and right indices are inclusive, and that's a really important thing to just be careful of, that you're kind of doing that right. Okay, so if the right and the left are basically the same amount, or basically there's only one index left, then to return that. Okay, now the idea is that I need to divide the array in half and sort each half. So I need to know the halfway point. So left plus right over 2. Now this is Python, so that is not going to be automatically floored. So I better go ahead and force it to be floored. Okay, then I'm going to, oopsies. Okay, let me try that again. I'm going to copy and paste that method. Okay, so if that's the case, then call on the left side, call it on the right side. Oops, middle, it's going to be middle plus 1 now because these are inclusive indices. And I'm going to give middle to the left side. Okay, call on the left, call on the right. And then I need to merge them. I'm going to call a merge back method. You'll note how I'm writing the sort of high-level structural code. That's a really useful thing to do in interviews as well, to make sure that you kind of get that structure out off the bat. Helps you also organize your thoughts. Okay, so I'm going to call this thing that merges the left and the right back into one array then. Or merge it back into, I'm going to have it merge it into a helper function. Okay, and then, so it merges it back, returns it into helper, and then I'm going to have a method that copies that helper array back into the original array. And so I'm going to need to know what that, so where in the array to copy it. So I'm going to need the left index. Okay, so that's my structure. All right, so now let me fill out these methods. So first up, I'm going to do merge back because that's actually sort of the interesting piece of the code, and like copying one array to another, not terribly interesting. And it's best in interviews to focus on sort of what's interesting, what's more core conceptually to the algorithm. Okay, so merge back is going to need it's going to need the boundaries of each side. So it's going to need the start of the left side. I don't actually need the left end and the right start because they're just off by 1 index. So I'm going to need the left start, the right start, and the end of the right side. I'm not going to call, I could have called right start middle, but then it gets confusing because it's a different middle because it's off by 1 before, so the right start is actually the old middle plus 1. So I'm going to call it right start, makes it more explicit. Okay, so then the merge function, what it needs to do is it needs to have a helper array. So I'm not going to do this in place. It's going to have some sort of helper array, and it's going to copy the left and the right side, which are already sorted. It's going to copy them in sorted order into the helper array. So I'm going to need an array of how long? So it's going to be the right end minus the left start. Now those are inclusive indices, so I'm going to need to do a +1. Okay. And then it's going to copy elements over. So for I'll call it index, I guess, for index from, in range. So I'm going to walk through the helper method and basically, helper array, and basically say, give me whichever one is appropriate. So give me left if appropriate, else give me right. So that's my basic idea. And then I'd want to return the helper after. All right, now for the details, of course. So how do I know when is the left appropriate? Well, I need to have indices that, some sort of index in the left side and the right side. So I'm going to need a left index and a right index. So left index, it's going to start off as the left side. Right index is going to start off as the right side. All right, so far so good. Okay, and then when is the left side appropriate? Well, this is kind of the sort of the general case is the left side is appropriate if the left side is smaller. Oops, then array start, left start. Sorry, not left start, left index. If the left side is smaller than the right side, copy over the right. And how do I copy? Of course, I just do helper of index equals array of left index. Else helper of index equals, else I want to copy over the right side. Okay, so that's the high level idea, but the details, of course, are incredibly, incredibly important. Okay, so one issue here is I have to, after I copy the element in, I better move that index over because that's already been copied. Same thing on the right side. Plus equals 1. Okay, now there's a whole lot of details here that are missed. So first of all, I don't want to, left index could be out of bounds, so I do not want to do this comparison if left index is out of bounds. So if left index is less than or equal to, well, I could do less than or equal to right start minus 1, but if left index is right, that left is less than right start and. So I only want to do that comparison if the left index is in bounds. So if it's broaching over to the right side, then don't do that. Okay. And then when else might the left index be appropriate? I also want to make sure that if the right index has gone out of bounds, so basically I've copied all the right sides over, then I want to always copy the left. So if right index is out of bounds, or the left side is smaller than the right, then copy that over. Okay, so if the right side is out of bounds, or if the left index is still in bounds and the left index is pointing to a smaller value, copy the left. Otherwise, copy the right. I don't need an else if here because I always copy one value or the other. I'm never completely done until I'm, well, completely done. So I always copy one value or the other. Okay, so that idea looks right. Now, let me do copy back. This one's pretty straightforward. I just need the array, I need the helper then copying it into the array, and then I need to know the offset. So some offset in the array, which is getting copied. So for I in range, so then I walk through the helper array and copy values over. So copy from I, helper I, that should be offset plus I. Okay. So let me walk through this code and see if this idea makes sense. Okay. So, I never even wrote I need a wrapper method for this merge sort. So merge sort, because I don't want to make my users have to call things with these indices. So it's going to call merge sort helper on array. The left index starts as 0. The right index, it's inclusive, so it starts as the length of the array minus 1. Okay, so I call that, and then I go up here. If I only have one element left, then there's nothing to sort, it's just a single element. Otherwise, find the midpoint, sort the left, let me check those indices are right. So left through the middle, and then just after the middle through the right. So sort the left, sort the right, merge them together, and I'm calling it with the start of the right index, which is middle plus 1. And then copy them back in. Is that offset right? Should it be left? Yes, it should be. Great. Okay. Now let me double check the merge back thing, array, or function. So create a helper method, or helper array. That is the far right through the far left, minus the far left plus 1 because of their inclusive indices. Okay. Start with my left and right pointers at the start of each side. Okay, and then walk through the entire helper method, helper array, and I always copy one value or the other. I copy the left value if the right is out of bounds, then I always want to copy the left. Or if the left is still in bounds and the left is pointing to a smaller value than the right, then copy the left. Otherwise, and then move the left. Otherwise, I always want to copy over the right, and so I move the right. Okay. All right, so this looks good. Let me try to run this and see if we got it right. Awesome, that looks actually sorted. Perfect. So merge sort is a useful algorithm to know, practice implementing. It has an n log n runtime in actually best, worst, expected, etc., all cases. And the reason why it's always that is that there's no randomness to it. There's no like, oh no, you could pick the wrong element. There's no randomization happening here. So you'll always do the same thing. And so it's always going to be n log n for the runtime. So another thing that's useful to do, I would encourage you to try implementing this yourself. Be really careful for those little boundary checks and the little indices. Problems like that are very easy to have little off by one errors on there, so always double check those. And then the other thing that can be a useful little fun experiment after this is see if you can implement this. This is a top-down recursive approach. See if you can implement this in a bottom-up way. It's a little bit different, but it's still the same idea. In fact, that's generally true with a lot of recursive algorithms. It's useful to, once you've done them recursively, see if you can do them bottom-up as well. It can sometimes be more difficult to write, a little bit more confusing to read, but it's a nice little thought experiment. So give that a go and see.
Hi, I'm Gail Lock-McDowell, author of Cracking the Coding Interview. Let's talk about what merge sort is. Merge sort is a very popular algorithm. Hi, I'm Gail Lock-McDowell, author of Cracking the Coding Interview. Let's talk about some tips and tricks for working with sorting. I'm not going to talk about what merge sort is or quick sort and things like that. I'm going to assume you already know that. But let's talk about just sort of some tips and tricks for working with sorting in interview questions.
First up, identifying when is a sorting problem. Sometimes it's explicit, so how would you sort the data like this? In other cases, we need to kind of figure it out, and comments or tip-offs that this might involve sorting are times when we need to find the first or the last or the ith biggest or something like that. But keep in mind that we may not do that through just sorting the whole data. Maybe we'll use something else like heap or binary search tree or something like that that has some ordering properties but are not conventionally sorting problems. When you do your interview, you should know both how to implement sorting algorithms from scratch, should it come up, because sometimes we may need to do a modification of merge sort or something like that. But it's also really useful to know how to just call the sorting algorithm in your language the way that's built in a way that allows you to change how you're sorting it, like knowing how do you sort a list of person objects by their age. You don't necessarily want to do that from scratch. It's much better if you can just leverage the built-in algorithm. So you should know how to use that. Also know how to, on a related topic, know how to do a forward as well as a reverse sort. So sometimes you might want to order things from smallest to biggest. Sometimes you might want to order things from biggest to smallest. Now, generally speaking, interviewers are not going to be too concerned if you don't know the syntax for this. But still, you're going to feel more confident if these little things aren't tripping you up at all. If you're implementing sorting from scratch, look for those boundary checks. A lot of errors happen that way, so be thoughtful on that. And then I would also recommend that you are familiar not just with bubble sort, quick sort, and merge sort, but some of these less common ones like radix sort and bucket sort, which are frankly pretty closely related. Because a lot of times in interview questions, we find that the best way to sort it is actually with some of these less conventional sorting algorithms. So I'd look up what those are and be comfortable with those as well. Honestly, the way that sorting comes up the most in interviews is actually as a step in another question. Not that your interviewer can't ask you sort the data by this, and sometimes that happens, but a lot of times it's just you need to use sorting to solve some problem. So that's why it's really important to be comfortable with different sorting algorithms and also be thinking about their space and time complexity. Because when you need to compute the overall space and time complexity of an algorithm, you need to take into account that sorting step as well. So you want to make sure you're comfortable with that. So practice those, look up those algorithms, and make sure they're just, top of mind so you know.
Hi, I'm Gail